Right. Our next application is a variation of the previous section. And let us write as follows. So A plus hat B. What is that? This is the sum of the values A pairs A, B, where A is in A and B is B in B, and these two things are distinct. All right. Now, the Erdős and the Heilbronn conjectured in 1964 that A plus A is at least minimum of P and twice A minus 3 for A subset of P. And this has been open for 30 years. So it was open for many years. And then it was firstly proved by Diaz da Silva and Hamilton in 1994 by using tools from representation theory. It's not easy. But however, 1 year later, Alon and Natanson and Lustra proved that this actually has an easy proof by using combinatorial strength. So that's what I'm going to show you. So here's the proof. So we're going to show you the proof by Alon and Natanson and Luza in 1995. All right, so we prove that if A is different from B, then A plus B plus hat B is at least minimum of min A plus B minus 2. Yes. So we're gonna prove it for more general version. Instead of A hat plus A, we're gonna have A hat plus B. Why is this okay? Because we can take A and A minus X, right? So A plus A minus X is equal to A plus A, right? I can remove one element. So that's why this is enough, right? This A plus B minus 2 is going to be 2A minus 3. Now we do the similar thing. We may assume the size of A plus size of B minus 2 is at most P. Why? Because otherwise, for all G in GP, I can look at the G in A, no, A, people in A and people in G minus B. And right, how can they interact? It may be possible that right, so if A plus B is bigger than P plus 3, right? That's what we are having, right? So if a plus b is bigger than p plus 3, then you're gonna have at least 2 pairs. So here in these 2 sets, if a plus b, no, at least 2. Right, how many overlap do we have? A intersection G minus B has size at least 3. Sure, right? And so that means I have a like A1 is equal to G minus B1, A2 is equal to G minus B2, A3 is equal to G minus B3. Now, and if we don't have a pair of an elements from A and elements from B whose sum is G, then this means that A1 is equal to B1, and this means A2 is equal to B2. This means A3 is equal to B3. Then what does that mean? You have 3 elements of the group whose, so A1 plus B1, A2 plus B2, A3 plus B3, all of them are actually equal to G. Maybe I'm wrong, or A plus B. I mean, the thing is, so twice A1 is equal to twice A2 is equal to G, so this means that A1 minus A2 is equal to A1 minus A2 is equal to and A2 minus A3, all of them are equal to 0. Right? Wait, that means A1 is equal to A2. It's not interesting. I don't know why I need a A3. So let me see. Why did I have A3? P plus 1, so right, so we have a yeah, so I think it's okay to have 2. Yeah, okay, but anyway, it doesn't matter much, but it's okay to have, I think it's okay to have this. Yes, well, it's okay. All right, so this means that we can assume that A plus B, it's actually, what could be better is just prove it for less than or equal to p. So otherwise, yeah, so that's better. Yeah. All right. Now, suppose that a plus b is less than or equal to a plus b minus 3. Oh, by the way, what's the conclusion here? Did I say the conclusion? The conclusion is that these two things are same. There's a contradiction, right? We can pick, by Pisonal principle, we can pick two distinct elements, right? Two intersection points here, but they are same. That's not possible. So whenever this is the case, that means any element G inside the GP can be written as a sum of distinct pairs. Right, so that the a hat plus b is equal to GP. Let me just write it down. Right, now we assume that. So let's say fx plus y is the product of x minus y plus x plus y minus c for c in C, where C is a subset of GP and it covers all a hat plus a plus b, right? And the, oops, size of C is a plus b minus 3. Now the degree of f is size of C plus 1, which is a plus b minus 2. The coefficient of x to the a minus 1, y to the b minus 1 in f is exactly what? So we need to choose, I mean, it could be that we choose a minus 1, a minus 2 from x, so x to the a minus 2 and then multiply x. Or we could choose b minus 2, oh, I mean a minus 1 for x and then multiply y, right? So this is like x times x to the a minus 2, or this is y times b minus 1, or this is y times x to the a minus 1 and y to the b minus 2. The coefficient of that, and this is the coefficient of this. And what is that? Right? So c factorial, what is c factorial over a minus 2 factorial and b minus 1 factorial minus c factorial a minus 1 factorial b minus 1 factorial b minus 2. So it's going to be the common term is c factorial, and now, well, a minus 2 factorial, okay, let's say a minus 1 factorial, b minus 1 factorial, and c factorial is common, and the term here you get a minus 1 minus b minus 1. So that's a minus b divided by a minus 1 factorial b minus 1 factorial c factorial. All right. Now we know that size of A is different from size of B. Right? Size of A is different from size of B. So this is not a multiple of P. This is not a multiple of P. Right? It's A plus B minus 2. A plus B minus 2, and this is less than P, right? So this is not a multiple of P. So therefore this is not a multiple of P. This means that the coefficient of that term is non-zero. So we can use the combinatorial null strand. What's the conclusion? There exists A in A and B in B, so that FAB is non-zero. Okay, and that means A plus B is not in C. So NAB are different. So A plus B is not in A plus B. That's contradiction. Okay, so that's the proof. Now, by using the same proof, you could prove generalizations easily. Let me skip that. All right. So that's it.